Aloha everybody, this is Gigi from Kauai Community College. In this video, I will be talking about basic integration techniques. So let's get started. It's going to be a long one. Okay, so first, suppose you have an integral that looks like this, where you have a sum on the numerator, all divided by 3x. You can then take each individual terms in the sum and divide by 3x to be able to simplify that to just x squared over 3. This x is going to cancel with this x right here, and it will just be 4/3. And then 1 over 3x, I split that into 1/3 multiplied by 1 over x. And the reason why I did that is because that's something that I know when I am taking integral, right? So does 1 over x ring a bell? Yes, that would be ln x, right? Now we take the integral of that. We'll get x to the third over 9 minus 4/3 x plus 1/3 ln of absolute value of x. And don't forget the plus c. And that is what we have seen in algebra classes as division of monomial, right? And the second strategy that we want to use is long division or polynomial division. Suppose you have x squared plus 3x plus 1. This time you are dividing by x plus 4. So you need to resort to this long division method to separate the fractions. Okay, so divided by x plus 4. Then we're thinking, what times x will give me x squared? Of course, that is x. Then we would multiply, right? And then that would give me x squared plus 4x. And then I would have to subtract because that's how long division works. Okay, so x squared minus x squared is gone. 3x minus 4x is negative x. We carry down the plus 1. Then what times x will give me negative x? And that would be negative 1. Negative 1 times x is negative x. Negative 1 times positive 4 is negative 4. Then we are going to subtract to get negative x minus a negative x is gone. 1 minus a negative 4 will give us 5. And 5 is our remainder, and we write remainder out of divisor x minus 4. So this fraction can be split into x minus 1 plus 5 over x plus 4, and we're taking the integral with respect to x. Okay, now go ahead, then take the integral. We have x squared over 2 minus x plus 5 as a constant, right? And then the integral of 1 over x plus 4 is ln of x plus 4. And don't forget your plus c. And that is how long division works. And that's why you had done long division in algebra classes, right? Now, next method is to rely on some trig identities. Okay, so back to pre-calculus now. Let's see if you remember your pre-calc. The integral of cosine square x dx. Well, that's not a derivative that I know of, so that I can go backward. So I'm thinking, well, if I can trade cosine square x into something that's a little bit easier to take the integration, then I would say, well, the thing that comes to mind is cosine square plus sine square equals 1. But that's not going to be helpful, because if you solve for cosine square x, in this case, you would get 1 minus sine square x, which, when you take the integral, well, what's the difference between sine square and cosine square, right? It's not going to be helpful. So this right here is not helpful. So let's rethink some other identities that we have. And one of those is the half angle identity. The reason why this is helpful is that it trades in cosine square for just cosine, even though the argument here in between the input right here is 2x. It's still helpful because it's linear, right? So that will be the integral of 1 plus cosine of 2x all divided by 2 dx. And then learn from the previous method, I can split those into 1/2 plus 1/2 cosine of 2x, right? So the integral of 1/2 dx is 1/2 x, and the integral of 1/2 cosine of 2x, right? The integral of cosine is going to be sine of 2x divided by the inside derivative of 2. So that makes it a 4 right there, plus c, of course. Okay, and that's how that works in trig identity. So if you have something that you cannot integrate, then look for some identity to replace it. Now, next method, we are using radical conjugate. Okay, so suppose you have x squared minus 16 over 2 plus square root of x. That's looking pretty nasty, right? Even if you try u substitution, it doesn't work very well right there. So the trick here is to go ahead and multiply by the conjugate of 2 plus square root of x. Okay, and you'll see after you multiply by 1, actually, that would be 2 minus square root of x divided by 2 minus square root of x. This right here, this part right there, is going to become 2 squared minus square root of x squared. That's the difference of 2 squared, right? And that would be 4 minus x. And that is nice because notice what you have up here. What you have there is x squared minus 16, right? And x squared minus 16 can be factored out to be x plus 4, x minus 4. So then that is going to divide out with your 4 minus x on the denominator. But then you say, oh, hey, that's not the same. One is x minus 4, the other one is 4 minus x. So they are opposite of each other. So what happened when you divide out? You get magic rainbow -1. Okay, so when you take this expression and multiply that back, and don't forget, actually, the -1 on the outside here, okay? You will get the integral of that. And I did forget the -1. So my answer is going to have to be multiplied by -1 there. When I multiply this out, x times 2 is 2x. X times square root of x is square root x to the 3/2, right? And then 4 times 2 is 8. And then 4 times negative square root of x is -4, x to the 1/2. And then again, don't forget the -1 that you have up front here, okay? And then so your answer really is, and my answer should be the opposite of whatever these are because there's a negative in the front. And then plus c. Okay, so the final answer should be -x squared plus 2/5 x to the 5/2 minus hx plus 8/3 x to the 3/2 plus c. That's your final answer. Sorry about that mistake. Okay, and that is how you use radical conjugate. Okay, next in the series is to use a trig conjugate. How does that look like? Something like this, right? We know that when we multiply by this conjugate, we will get 1 square minus sine square x, and 1 minus sine square x is going to give you cosine square x. That's the Pythagorean identity, right? So that then becomes 1 plus sine x on the numerator, and the denominator right here is going to become cosine square x. And then we're going to apply the first thing that we have learned, meaning to split, right? And what you must remember is that secant is 1 over cosine x. So then what you have right there 1 over cosine square x is going to be secant square x. And that's nice. That's something that you can take the integral of. And then the next term right there, you have sine of x over cosine square x, right? That is going to equal to 1 over cosine multiplied by sine x over cosine x. And something from there is that sine x over cosine x is going to give you tangent. So your integral will be the integral of secant square x dx plus the integral of secant tangent. So then the integral of secant square is going to give you tangent x. The integral of secant tangent is secant x, and don't forget the plus c. Okay, so that's how trig conjugate come into play, so that you can apply the Pythagorean identity, and then you can move forward with that, right? The next method is completing the square. Completing the square. Now, what's the idea here? Why do we want to do that? Okay, so let's just stay with me for a bit and you'll see. I'm going to complete the square so that I can turn the denominator into something nice. Okay, x squared plus 6x plus 10. Now, if you have 6x, you're going to wish to have 9, right, to make a complete square. Half of 6 is 3, square it, it's 9. So then you wish to have x squared plus 6x plus 9. So this 10 is going to be split into 9 plus 1. Therefore, x squared plus 6x plus 10 is going to equal to x plus 3 squared plus 1. So your integral will be 1 over x plus 3 squared plus 1 dx. Now we would have to know, well, why is that helpful? Well, that has to do with inverse tangent. Okay, let's take a look. Suppose you let u be x plus 3, then your du will just be 1 dx. So you can replace this, do a little u substitution here. That becomes the integral of 1 over u squared plus 1 du. And that's just straight derivative of inverse tangent u. So then if you go back and put your x plus 3 back into where the u is, then your answer would be the inverse tangent of x plus 3 plus c. Okay, and that's a really good trick. Why did we want to complete the square? We want to complete the square so that we can get this integral right here that looks like inverse tangent. Okay. Now, sneaky you, this is fun. Sneaky you is kind of fun. If you take a look at the expression right there, what do you notice? Well, the first thing that would be staring at you is the negative exponent, right? So you're thinking in your head, well, what's negative exponent? That's 1 divided by e to the x. So really, I have a fraction right there. That really is 1 over 1 minus 1 over e to the x. And if I have a complex fraction, I can multiply both the numerator and the denominator by a common denominator so that I can clear up all the fractions, right? That's what complex fractions are. So then we would multiply both numerator and the denominator by e to the x. So then I will have, okay, on the numerator, I have e to the x. On the denominator, e to the x multiplied to 1 is e to the x. E to the x multiplied by e to the negative x. Keep the denominator the same. That will give me e, right? And then add the exponent. Negative x plus x is going to be e to the 0. And e to the 0 power is 1. So this integral will be just e to the x over e to the x minus 1. So then we can now do a nice little u substitution, right? let u be e to the x minus 1, then du will just be e to the x dx. And that is nice because that right here is du, right? So then you will have the integral of 1 over u du, and that will give you ln of u, absolute value of u, plus c. So then go back and substitute the x back into your substitution, then to your u. Your integral from the beginning, the original integral, will equal to ln of absolute value of e to the x minus 1 plus c. And that is how we do integration. Those are the basic techniques of integration. So remember, you have 1, 2, 3, 4, 5, 6, 7 different things to try before you can move on to some other methods. Okay, and that's it for today. Sorry for the long video, but those are all the basic integration techniques.